Good morning, everybody. Hello again. Today we are going to start our second day of our virtual congress sections. We are going to start in a few minutes the third section with Professor Jinyang Xu from China, Shanghai Jiao Tong University. He is the invited speaker of APMAS Congress. And he's going to present his presentation as live. Professor, are you ready? If you are ready, we can start the record and you can start your presentation.
Thank you, Chairman. Okay, so I will start my presentation now, and then I will share my screen.
Okay.
Would you please give me the access to allow me to share the screen?
Okay, we did it.
Okay. Okay, so now I will start my presentation. Today is my great pleasure to attend the 10th International Advances in Applied Physics and Material Science Congress and Exhibitions. My name is Jinyang Xu. I'm coming from Shanghai Jiao University, and today my presentation concerns the drilling studies of high-strength CFRP composites using the specialized drills. Before starting my speeches, I would like to make a brief introduction on myself. And I'm currently an associate professor at the Shanghai Jiao University, and my current research interests focus on the mechanical machining, materials processing, as well as the numerical modeling of different types of manufacturing processes. I'm currently also serving as an editorial board member of several international journals such as the Simulation, the Advances in Material Science and Engineering, as well as the International Journal of Aerospace Engineering. The next slide is just to present the contents of my current presentation. I will start my speeches following this sequence. So in the subsection 1 introduction part, I will introduce the industrial background, as well as the machining challenges faced by the current manufacturing sectors when dealing with the carbon fiber reinforced polymers. And then some tool solutions to deal with the difficulties encountered in the composite materials will be presented. And after that, the subsection 2 will deal with the experimental procedures, as well as the details of the used cutting tools, as well as the process parameters. Then I will focus on the subsection 3, the results and the discussion part. I will discuss the machinability behavior of the high-strength CFRP composite in terms of the different cutting responses. And finally, we can get some key conclusions and future perspectives regarding my current research work. Okay, I will start the subsection 1, the introduction, the industrial background of the carbon fiber reinforced polymers. So in the modern industry fields, we can see that the use of the carbon fiber reinforced polymers has been increasingly developed in a variety of industrial fields, such as the wind power, the aerospace engineering, the automotive fields, as well as the energy and electronics fields. So why did carbon fiber composites become so attractive in the industrial fields? We know that the carbon fibers are basically consist of two disparate phases. The one is for the reinforcing fibers, which provide the main properties of the commodity materials, and they often exhibit the high abrasiveness, high hardness, and brittle fracture. And on the other hand, the matrix polymers basically shows the poor thermal conductivity as well as the low elastic modulus. So since the two types of constituents exhibit disparate mechanical physical properties, they lead to the anisotropic machinability. If we look at their industrial background in the military aircraft, it is very clear that there is an increase of the demand for the use of the advanced high-strength carbon fiber polymers, particularly in the military aircraft, in the past few decades. And if we look at their applications in the commercial airplanes, for example, the new generation Boeing 787 Dreamliner, and we will see that the commodity materials basically has taken about 50% of all the material distributions in such advanced commercial airplanes. So this highlights the importance of the use of the high-strength commodity for the aerospace industries. And in addition, if we look at the new generation, the Airbus, the A380, and we will see that the high-strength commodity materials basically have been utilized for the fabrication of the keynote cabin components or structures in the advanced aircraft, such as the vertical tailplanes or the floor beams. So some people will raise some questions about what's the difference between the conventional CFRPs and the high-strength CFRPs. So this slide is I just present some types of their different characteristics. Okay, so the high-strength CFRP commodities basically exhibited extremely higher strength, higher modulus, and higher stiffness. By contrast, the conventional CFRP basically shows a moderate strength, modulus, as well as moderate stiffness. So the machining of high-strength CFRPs shows much difficulty, more difficulties than the machining of the conventional CFRPs. And additionally, since the use of the commodity materials requires a drilling process to create the holes for assembling the different commodity structures into a functional assembly. So there is a critical demand for the high quality drilling of the CFRP holes. And it is well known that the commodity materials basically exhibit the anisotropic behavior and the heterogeneous architectures. So these two types of factors just raise some key challenges to the manufacturing communities. And here I just list some of the important issues associated with the manufacturing process for the commodity laminates. For example, machining the high-strength commodity materials will entail the severe delamination damage, a higher risk of glass transitions for the polymer matrix. And it should also be noted that the delamination damage is regarded as a critical failure in the scientific literature, and it accounts for nearly 16% of all the commodity part rejections, particularly in the aerospace fields. And in addition to the delamination damage, machining of the high-strength CFRP commodity also entails a rapid tool wear in the form of edge rounding. And the below figures just shows some morphologies of the enlargement of the cutting edge residuals after the drilling of the commodity materials. So such a phenomenon will result in a shorter tool life, as well as an increased machining cost. And the low manufacturing efficiency. So how to cope with such difficulties encountered for the component machining? The potential solutions is the design of functional tools dedicated for the component machining. The tool designs can also be divided into procedures. The one is for the modification of the tool geometries, such as change or modify the tool chisel edge zones. And another method is for the selection of advanced tool materials in order to offer sufficient hardness to resist against the abrasion wear. So the topic is just leads to the key objectives of the current presentations. So my presentation will focus on the study of the specialized drill bits on the drilling machinability of high-strength and CFRP commodities. And secondly, we will seek to inspect the dominant wear mechanisms governing the manufacturing of the high-strength commodities. And finally, we will seek to evaluate the effectiveness of the specialized cutting tools for the commodity machining. Well, we will move to the subsection 2. The subsection 2 is focused on the experimental procedures and details for the drilling operation. And this slide just presents the utilized machine tools as well as the utilized the CFRP specimen. So the drilling studies were carried out without coolants on a Hooker CNC machining center. And the test specimen are multi-directional carbon epoxy laminates constituted by the T800 high-strength fibers and the X850 resin matrix, having a total thickness of 9.16 millimeter. This is for the thickness, okay? And the utilized cutting tools are specialized drill bits. The first cutting tools is the CVD diamond-coated tools featured by two protruding edges at the drill periphery with the pointer angle of 180 degrees and a helix angle of 38 degrees. And the second cutting tools is the conventional twist drill. And the third cutting tools is the duck drill. It is featured by a two-stage point design with a corresponding helix angle of 10 degrees and a 64.89 millimeter length for the chip fluid. And the below tables just summarize the machining parameters selected for the manufacturing processes. And here we just utilized a full factorial design of experiments, including the 4 types of spindle speeds and 4 levels for the feeder rates. Well, during the machining of the high-strength CFRP commodity, we will seek to identify or evaluate their drilling responses. So here I just summarized the key machining responses that have been addressed in our work. Firstly, we will investigate the cutting forces by a dynamometer. And secondly, we will evaluate and quantify the drilling-induced delamination damage using the scanning microscopy. And then the CFRP hole surface and tool morphologies were characterized by SEM. And eventually the hole diameters and the cylindricity errors were quantified by a CMM. So after the end of the experiments, we will seek to identify the parametric effects on the drilling responses of the high-strength CFRP materials when using the different types of specialized drill bits. And this slide just presents the results of the thrust force as a function of the different machining parameters, as well as for the different types of the drill bits for the bullet spur drills, the twisted drills, and the duck drills. And through the three types of figures, it is clear that the feed rate has a positive impact on the development of the thrust force. And we can see there is a linear increasing correlations between the thrust force and the feed rate. And additionally, the bullet spur drills basically produce the lowest thrust force, followed by the twist drill and the duck drill. And if we look at the bottom figures, okay, we will see that the force signals will develop very rapidly during the engagement between the tool edges and the workpiece specimen. And after that, the cutting forces will suffer a steady variation. And this means the cutting edges have been fully engaged into the composite materials. And finally, when the drill edges comes to exit the composite laminate, we will see there is a rapid decrease of the cutting force signals. Additionally, we also carry out some SEM observations inside of the cutter hull wall morphologies. And here in this slide presents the three types of the morphologies for the machined hulls when using the different types of cutting tools. So it is very clear that if we use the bullet spur drills, it basically promotes much fine, much better, and much smooth composite hulls with a minimal damage formation. Additionally, the duck drill basically promotes the poorest composite hull surface. So this is for the duck drills, okay? So we can see that the cut surface by the duck drills basically featured by a large amount of drilling-induced damages, including the interlaminar delaminations, the crackings, and the severe push-out delamination damages. So through the comparison of the whole morphologies, we can infer that the duck drills is not effectively for the manufacturing of the high-strength composite materials. Additionally, we also use the SAM equipment to identify the interlaminar delamination damages occurring inside the hull walls. And the first image is just for the bullet spur drills. So we will see that from the entry side to the exit side, we will see that when the drill edges approach to the exit side, there is an increasing extent for the delamination damages, okay? And basically, machining the composite entails the formations of the severe delamination damage, which is a key factor accounting for the rejections of the final composite materials. And additionally, if we look at the results obtained by the twisted drills, okay, and basically the similar phenomenon can be obtained during the manufacturing processes. And here, if we look at the first plies, and here, please note that the first ply indicated the last pliers at the exit side of a cutter hull, okay? And we will see that the distribution of the delamination damages basically shows some symmetric laws around a hull peripheral, okay? And this phenomenon is basically associated with the fiber orientation dependent properties of the studied composite materials. And finally, if we look at the results obtained for the duck drills, okay, so we will see that there are a lot of damaged areas around a cutting hole, okay? And it basically indicates that the dark drills is not effective for reducing the delamination damages for a community laminate. Finally, we also seek to quantify the delamination damage. The delamination damage extends with respect to the utilized process parameters as well as the utilized the drill type. Okay, and here we will see that there is the linear correlations between the thrust force and the delamination damage, irrespective of the used drill types. Okay, and besides, if we look at the bottom figures, it is very clear that the braided sprue drills basically generated the least delamination damage, such as a lower delamination factors in comparison with the other two types of cutting tools. Moreover, we have also made efforts to identify the hole diameters of a cut community laminate under the use of the different types of the drill bits. And here we will see from this chart that basically the twist drill here. This bar indicates the twist drills. Okay, so the twist drill basically produce the hole diameters being lower than the nominal hole diameters. And by contrast, the dark drills basically produce the much lower hole diameters compared to the nominal ones. And by contrast, the braided sprue drills basically produce the diameters much consistent or close to the nominal hole diameters. So this comparison indicates that the use of the braided sprue drills may benefit the production of more consistent hole diameters for the high-strength composite materials. And the next figures just present the effects of the feeder rate on the machining on the hole diameters when using the different type of the drill bits. Okay, and basically increasing the feeder rate tends to enlarge the hole diameters. And the braided sprue drills also produced the much consistent hole diameters than the other types of drill bits. Moreover, we also tried to find out the parametric effects on the cylindricity areas of a cut community holes. And here, if we look at this image, we will see that in general, the braided sprue drills basically produced the lowest values of the cylindricity areas compared with the other two types of drill bits. And in contrast, the dark drill basically produced much higher values for the cylindricity areas, which indicates a much poorer hole dimensional accuracy for the cutting tools. Finally, we also sought to identify the dominant tool wear mechanisms governing the tuning of the high-strength composite materials. So when machining the high-strength composite materials, one of the key challenges is the rapid tool wear that leads to a short tool life as well as the increased machining cost. And here, this image just shows the obtained results of the SEM morphologies for the worn tool edges for the braided sprue drills after the drilling of the high-strength CFRP composites. And we will see that even after the making of 8 composite holes, the braided sprue drills can remain remain intact without suffering the severe damages or the fracturings during the manufacturing processes. And we only identify a small amount of coating peelings or some evidence of the adhesions of the chipper dust onto the drill flank surface. And by contrast, if we look at the wound surface morphology for the twisted drill, okay, the twisted drill, and we will see that the twisted drills basically suffers the severe welded chips, particularly at the drill chevrons. Additionally, there are also some evidence for the occurrence of the edge rounding, particularly due to the high abrasiveness of the carbon fibers. And also, we also find enlargement for the flank wear widers. And some types of the chip adhesions are also observed on the tool flank surface. Finally, if we look at the SEM morphologies for the dark drill, the last drill bit, okay, we will see that there is a lot of adhered dust and the fracture edges and edge rounding features can be observed onto the drill edges. And this means the cutting tools undergoes the severe or harsh cutting conditions during the tool chip at the tool chip interface or the tool workpiece interface. So from the mechanisms and from the observations of the tool wear morphologies, it also indicated that the dark drills is not favorable for the drilling of the CFRP composite. Well, so the above discussions about the manufacturing responses following the composite materials machining process, we can obtain some key conclusions. And firstly, the machining of the high-strength CFRP laminates basically produce the various types of thermally and mechanically induced damage. And secondly, the wear mechanisms of drilling high-strength CFRP composite are abrasive wear. This is due to the high abrasiveness of the carbon fibers. And the abrasive wear can lead to the edge rounding of cutting tools and adhesion wears, probably due to the powdered chipper welding. And third, the bullet spur drill is confirmed to yield the best machining performance, followed by the twist drill and the dark drill. Our results also highlight the importance of developing functional designed cutting tools for achieving the damage-free drilling of high-strength CFRP composites. And finally, so the present investigation, we can also draw some future perspectives for the future works, okay? And particularly in order to cope with the difficulties encountered in the drilling of high-strength and composite materials, the manufacturing sectors need to optimize the tool geometries and the coating materials that match well the machinability of the CFRP materials. And in the second step, the manufacturing engineers have to develop the more cost-effective strategy for the high quality and high efficiency machining of CFRP laminates. And finally, there is also a critical need to apply the advanced manufacturing techniques such as the clean manufacturing, green machining, or the non-traditional manufacturing for the fabrication of the carbon fiber reinforced polymer composites. Besides, the next slide just shows some relevant publications pertaining to the topics discussed in my current speeches. Okay, and we also acknowledge the findings from the National Natural Science Foundation of China and also the Shanghai programs, which gives a lot of funds to support the experiments and the theoretical work of the current investigations. Okay, so that's all. Thank you for your kind attention.
Thank you, Professor. Thank you for your nice and very interesting presentation for high-strength composites for drilling technology. Just now, I want to ask all our participants, do you have any question? If you have any questions, you can write your questions to chat section, or please write the chat section. You have a question about you have a question. We can open the voice of your system, and you can ask your questions by yourself to Professor Jinyang Xu. Yes, we can wait a few minutes. I think there is no question for now. Thank you, Professor, again for your nice presentation.
Thank you, Chairman. Thank you.
Yes. If any participant want to ask any question, you can send email to Professor Jinyang Xu.
Yes.
Yes. Thank you again, Professor.
Thank you. Bye-bye.
Bye-bye.